So this is the first of two videos dealing with the concept of polymers. And before we get going, before we look at the reactions involved, I did just want to show you a couple of examples. I looked around my house. It took me about a minute to find a whole range of examples. So I just have a couple here. So here's an example. This is actually a molecule of propene. Double bond, single bond, 3 carbons. We'll actually revisit this one in a minute. But the plastics that make up this model for this modeling kit, all the plastics involved are examples of polymers. Different type of plastic, probably the same polymer though. My daughter's Perry the Platypus DVD, and the outside there's plastic on the outside. The case is plastic. The DVDs are a different sort of plastic. All different types of polymers, but potentially made from the same general molecule. This shirt I'm wearing is actually a polymer. And finally, found this up in the kitchen, pumpkin. Pumpkins certainly have quite a few different biological polymers in their flesh and skin. So you do not have to look very long and far to find all kinds of different polymers. It's a huge component of the chemical industry at the moment, making up different types of polymers for all the different products that are made up from them. So, a few definitions to start with. Pretty straightforward. A monomer, this is what makes up polymers. They're typically relatively low molecular mass molecules. And they get linked covalently, so it is covalent bonding, and when they get linked covalent, you link enough of them, you get a polymer. And a polymer then is a molecule with a large molecular mass. This can be a huge mass, millions of AMU, and consist of many monomers, not surprisingly. And then polymerization is just the process, the reaction that allows for the bonding of monomers to form polymers. So a few definitions. All right, let's have a look at a few. Oops. First type of reaction, addition polymerization. So this should ring a bell to you. Addition polymerization. Essentially, simple alkenes get polymerized. So these alkenes can have different functional groups, and so the functional group is going to determine to some extent the physical properties of the polymer. But that's not the only thing. But it's certainly one of the driving forces beyond physical properties of polymers. And so addition again is where we add across a double bond, a carbon-carbon double bond, and that is what allows for polymerization. And this occurs because of what's known as free radical polymerization. So addition polymerization, one way it happens is via the formation of free radicals. So there's 3 steps involved, an initiation step. And in this step, the alkene that's going to be polymerized basically links with some other molecule, and in so doing becomes a free radical. And a free radical is essentially something, a molecule, in this case an alkane, with a single free electron. And I've mentioned this before, free electrons do not hang about very long. They usually very quickly react with something. And so when they react with something, they get propagated. The molecule gets added to, and so the propagation steps occur a lot. There's many of them, but again, it's propagation a small molecule at a time. So the free electrons of the free radicals combine with another molecule to form a covalent carbon-carbon bond, and so you go from alkenes to polyalkanes. And then the termination step, not surprisingly, is just the step at the end, and that stops chain growth. And essentially chain growth gets stopped when 2 radicals, each with a single free electron, combine. Then there's no radical left and the chain formation stops. So here's just a few diagrams to kind of show you what's happening. So this is ethene. So ethene's a pretty common starting point for polymerization. And so ethene, when it reacts with some molecule to form a radical, ends up looking like this. So notice the free electron. So free electron, meaning this is very reactive. And it can actually cause other alkenes to break that double bond. And the other thing to notice is that it's now an alkane. So that double bond has broken. And so the radical is actually an alkane radical. And so now what happens is this alkane radical can influence a neighboring alkene. And so it's really at this area here with that free electron causing this bond to open up. And when it opens up, one of the electrons of that covalent bond becomes a free electron with on this carbon 1, and the other one becomes a free electron on carbon 2. And so that bond is gone. You're left with this radical alkane, and a covalent bond is going to form between those two electrons, leaving this end of the molecule as a radical. So it can continue to react. So it can go ahead and influence another alkene. And so here's my butane radical. So the butane radical gets formed when two ethenes interact and break the bond. And so there's the 2 carbons of that first ethene. There's the 2 carbons of the second ethene. Here's the bond that formed between them. It's a single bond. And notice that it's still a radical. There's a free electron. And so that's a process just carries on and on and on and on. So that's known as free radical polymerization. So the ones we're going to talk about now, that's one of the ways they get formed. First one is probably the simplest polymer. Polyethene. Common name is polyethylene. And there it is. So ethene, C double bond C. And so it polymerizes, as I just mentioned, via free radical polymerization. So there are 3 repeating units of my ethene in my polymer. And so N is going to be very large. So we just get polymerization for ages, and you get these very long chain molecules. Now there's a lot of uses for polyethylene. And it ranges from this range, very low density polyethylene, VLDPE. And so you've all seen this, frozen food bags, stretch wrap, saran wrap, that sort of thing. Pretty pliable, pretty soft. It's reasonably strong, but you can poke your finger through it. So you know, it low density, and not a super strong polymer. Right up to ultra high molecular weight polyethylene, and this is really solid stuff. You butcher's block or those white cutting boards you've seen, that's this high molecular weight polyethylene. Bulletproof vests have this material in it, so it's really strong. Components of hip and knee joint replacements. These things are lasting for many, many years inside the human body now, so this is a quite a durable polymer. Very different to saran wrap, but in essence made from the same starting material, from the ethene. So polypropylene, it's another very common polymer. I'm sure you've heard of that. And so the starting point for polypropylene is propene. And so one thing you want to be able to do is take a monomer like propene and be able to draw repeating units of the polymer. So the best way to do that, and you've noticed how I've drawn this here, and this sometimes helps, I sort of made that carbon 3 look like a methyl group. And if you do that, it becomes pretty easy, because there's the 2 carbons of the double bond, and that's going to open up to form a radical. And there's my carbon 3 with my methyl group. So this is carbon 2 that I'm drawing from now, and I bond another ethene. And I go and bond another ethene. And so having that carbon 3 of the propene as my as making it look like a branch makes it a little easier to sort of see where the repeating units are going to start. And so that is polypropylene. And so common uses for polypropylene: plastic cups, camping cup, those sorts of things. These really cheap gloves you can pick up at the end of the aisle, and money. So I remember when I was in Australia probably 25 years ago, they introduced their polymer money, and Canada just introduced it this past year. But it is long-lasting money, and it's also quite hard to counterfeit. So that's another reason why they made it. So that's polypropylene. PVC, polyvinyl chloride. Again, here the chlorine naturally looks like a branch because it is a branch. And so drawing repeating units of PVC is pretty easy. So there's my repeating unit of PVC. And PVC is, again, a very common material, wide range of uses. This one's been around for quite a long time, as evidenced by the record. PVC can be very durable, quite dense, quite heavy. Part of the reason for that is that's a polar functional group, so you're going to get dipole forces between polymers, between those strands of polymers. So that's a pretty strong force. These sort of plasticized, rubberized fins, things like that, I'm sure you're all aware of. And a very common use for PVC is with piping. It has replaced copper piping in a lot of instances for a couple of reasons. One reason is it's very easy to make. Copper now is getting pretty expensive. PVC piping is easy to make. It's very light, so transportation costs are significantly less than they would be for copper, and it's quite inert, so it doesn't really break down. And the copper actually is pretty non-reactive as well. Polystyrene or styrofoam. We've all heard of this stuff, and we all know it's really lightweight. And here's why it's really lightweight. There's that great big benzene ring as a branch, and so a polymer of polystyrene is a great big thing in terms of its area. So they can't get very close, unlike something like PVC with a polar group and a pretty small, relatively small atom as a branch. You got this big phenyl ring sitting out there, and that's going to hinder how close these polymer strands can get to one another, and so that makes it certainly fairly not very dense at all. And so it's lightweight, as this picture down here shows, with the gentleman pulling what appears to be a huge amount of styrofoam around on his bicycle. But it's also a pretty good insulator. Coffee cups are not very good at thermal conductivity, don't conduct heat very well, and so polystyrene is good as an insulator. Good as a packing agent because it's kind of pliable, so it'll sort of bend and squish and break, but not cave in all the way. Polyacrylonitrile, quite a common polymer, especially for fibers. It can be woven into fibers, and then those fibers can be used to make all kinds of clothing materials and all kinds of things. Common use for polyacrylonitrile is in wigs, so it looks quite a bit like hair if you make it correctly. So, and also, but it can also be quite strong and durable, as seen by the use of coverings for tents. So polyacrylonitrile is another example of a polymer. So all these examples are polymers that originate from an alkene. So you break that double bond, and you can add these small molecular mass molecules together to form long chains. Now, one thing you want to be able to do is identify the monomer. So here's an example. What's the monomer here? And as I said before, if you look at a branch as part of the monomer, that sometimes makes it a little easier. So here's a carbon with a branch, and so here's probably the other carbon, which means this was the C double bond C. And so here's a neighboring molecule, and it also has a C double bond C right here. And so I'm just going to draw the top two with the C double bond C are next to each other. And so if this one opens up, it's going to get a free electron and a free electron. and this bond is going to disappear. Well, that can now influence this bond, and it's going to cause this bond to open up and have 2 free electrons. And so there is where the bond forms. And so that bond was right up there at the top. And so this second free electron, carbon with the free electron, will form another bond, and another bond, and another bond. So that's the process. So we've identified the monomer here, so it's a 4-carbon monomer. And we can see here, this is where the double bond was. And so it's on carbon 1. So that monomer would be called but-1-ene. And they're the hardest ones probably to find. The simple alkenes are the hardest ones to determine the monomer for. If you have a halogen or a phenyl group or something like that, they're a lot easier to spot. But you do want to be able to try to recognize those different monomers from a polymer. And that concludes this video.